Here we go. So when we're talking about intermolecular forces, you guys, there's a difference between intermolecular and intramolecular. So the word inter means between, okay? And because I can't see you guys, since I hit all of your faces, if anything's screwed up and you can't see something or you can't hear me or whatever, maybe up in the chat or something. Okay, so what was I talking about? I was talking about this prefix inter. Like, what does this prefix inter mean? This Latin prefix means, means between. So when we're talking about an intermolecular force, we're talking about the force of attraction between covalent molecules. We are not talking about the bonds within the molecule itself, okay? So if I'm talking about like, well, don't draw this, but if I'm talking about, well, what's holding together, this molecule of H2, the bond holding this together, that covalent bond, we call that an intramolecular force. The force holding together the inside of the molecule, holding one atom to another atom. That's intramolecular. But there is a force of attraction, granted it's very weak, between one molecule of H2 and another molecule of H2. Now this is a gas, so obviously the force between them is very weak, but there is this force of attraction between these two molecules. And the force of attraction between these two molecules is what we would call the intermolecular force that we're going to talk about right now. Okay, so intra is within, inter is between, right? So like the dashed attraction between the molecules. Now, the other thing that I want to sort of clarify for you guys is this is only for covalent. When I'm talking about the dispersion and dipole-dipole and hydrogen bonding that we're going to talk about today, that's only for covalent molecules. The forces that hold together ionic substances and metallic substances and covalent network solids, these forces of attraction are different. We don't say that ionic has dispersion forces, okay? The force holding together a sample of an ionic compound is a crystal lattice structure, which is both the intramolecular force, the ionic bond, and the intermolecular force. Like if we think about a crystal lattice structure, the force holding together the cation to the anion is the same force holding together one unit of that salt to another unit of that salt. So for ionic compounds, we don't talk about intra versus inter. We just say it's held together by a crystal lattice structure. Same thing for metallic with your sea of electrons, right? You've got your cations or, your metal atoms. You don't need to draw these. You guys have these. You've drawn these a million times, just reminding you, right? The force that's holding together a sample of a metal is this sea of electrons. And this one we didn't talk about so much. A covalent network solid like diamond or graphite, silicon dioxide, is actually covalent bonds. Okay, so the thing that's holding together the molecule itself is a covalent bond, but the intermolecular force holding this one to this one is also a covalent bond, which is kind of wild. This is why diamond is such a strong structure, because you've got a carbon bonded to a carbon, bonded to a carbon, bonded to a carbon. So the whole thing is covalently bonded. That's why it's called a covalent network solid. Okay, so these are the forces that hold together ionic and metallic and covalent network solids. Now we want to talk about what are the forces that hold together just plain old covalent compounds. What holds this hydrogen molecule next to this hydrogen molecule? Now, before we get to that, let's talk a little bit about states of matter, because intermolecular forces are going to play a really big role in determining states of matter, determining transitions between states of matter. So let's look at our state of matter diagrams here. And we've, done this a million times. So, draw them, don't draw them, whatever you want. If I'm looking at 3 different substances that are all at the same temperature and pressure, right? Because temperature and pressure determine state of matter. You know, why would it be that this thing is a solid and this thing is a gas? Like if these substances, one is a solid and one is a gas at the same temperature and pressure conditions, it must be because the thing that is the solid has a stronger intermolecular force. Like there's stronger attractions, which is why in a solid, the particles can only vibrate. And they have set shape and volume. Versus something that at the same temperature and pressure is a gas, must have weaker IMFs, which is why the particles can expand and compress and collide with one another. And they have variable shape and volume. Now, those are your 3 standard states of matter. We can actually go past this. There are things denser than solids. They're a new state of matter discovered a couple of years ago called Bose-Einstein condensates. And of course, we know that gases, should you heat them and superheat them so that they collide and exchange electrons, gases can become plasmas. So like this state of matter sort of scale can expand beyond these 3 states of matter, but these are obviously the 3 that are the most important to us. I feel like there was something else I wanted to talk about states of matter. No. When we're back in school, hopefully tomorrow, I'll show you guys a demonstration of how temperature and pressure both contribute to state of matter along with the intermolecular force that's present. Okay, so when I'm comparing, like this has a strong IMF and this has a weak IMF, this comparison could only happen if we were at the same temperature and pressure. So, you know, the state of matter that something is in is going to depend not just on the IMF, but temperature and pressure conditions. It's like these competing forces. You know, the kinetic energy of the molecules is competing with the IMF that is holding together the atoms in the sample. So if your kinetic energy is greater than the IMFs, you're going to get that change in state. Okay, so you can think about the kinetic energy of the sample is competing with the IMF that's present, as well as the pressure, right? So when you push down on a substance, that pressure is helping out the IMFs, okay? So competing with the IMFs and pressure. So if you have more pressure, that substance is more likely to be a solid in most cases. And if you have less pressure, it's more likely to become a gas. So this kinetic energy of the sample is competing with the forces of attraction between the particles, which of course can be helped out by the pressure. I'll pause for a second here. All right, so let's move on and start talking about these different intermolecular forces. There are 3 main types that we are going to talk about. And I have some images. Don't necessarily draw the images, you guys. I'm gonna draw, hand draw a diagram, but you guys know, I just really struggle with this drawing this stupid shape right here. So that's why I put the images, but you can just draw what I draw for these. Okay, so the first of our IMFs is called dispersion. And like I said before, the reason why we have to talk about IMFs are because they help us determine properties. Okay, so these three main types, dispersion, dipole-dipole, and hydrogen bonding. We are going to talk about a fourth. But these three main types depend upon the identity of the substance and whether it is polar or nonpolar and how polar it is. Okay, because obviously the thing that's going to attract one thing to another, the only type of attraction we have in chemistry is this positive negative attraction. So it's going to depend on how polar it is. That's going to be the force of attraction that we're talking about. Okay, so it depends on identity and its relative polarity. And like I said, the strengths of these IMFs are different. Okay, so like dispersion is technically our weakest IMF and hydrogen bonding is our strongest. But what we didn't really talk a lot about last year, which is going to be really important this year, is even if you're talking about a weak IMF, like dispersion forces, that weak IMF can be made stronger. Like there are relative strengths even within the category of dispersion forces. So like last year we were like, okay, well, dispersion forces are weak and dipole-dipole are a little bit stronger and hydrogen bonds are the strongest. Okay, so like we talked about this as relative strength of those three main IMFs. And of course, you know, ionic bonds and, you know, your crystal lattice structure and your covalent network structure, much, much stronger. Like, so if we were to keep going past, you know, the strength of the IMF and the covalent substances up to ionic compounds and covalent network solids, those are even stronger. But what we're going to talk about this year that we probably didn't talk a lot about last year is that, yeah, dispersion forces tend to be weak, but there are factors that can make dispersion forces stronger. In fact, the dispersion forces can be made even stronger than hydrogen bonds. You're like, what? But you told me hydrogen bonds were strong. I know. You're not going to have to like memorize situations in which dispersion would be stronger than hydrogen bonds, but you might have a substance. Like they might give you these two substances and they're like, look, this thing only has dispersion. This thing has hydrogen bonds. But the thing with the dispersion forces is displaying properties that tell us the dispersion forces are much, much stronger. Well, what might some of those properties be? Well, melting point, boiling point, vapor pressure, viscosity, all these things I've listed off to the right there. So like, if the thing with the dispersion force has a higher boiling point than the thing with the hydrogen bonds, what the heck is going on there? It must be that there are some factors that are making those dispersion forces a lot stronger than we would otherwise expect them to be. Okay, so yes, this is your relative strength, but they can be made stronger or weaker on some key factors. And we're going to talk about each of those key factors as we talk about each of the different forces. And what are some of those properties that are going to be really important to us? State of matter, melting point, boiling point, vapor pressure. We haven't really talked about vapor pressure before. We'll talk about that another day. And viscosity or stickiness. Other ones, oh, I forgot some, like surface tension, adhesion, cohesion, right? In other words, I'm talking properties here, people. And then you just got to kind of like think about it. If there's a strong IMF, you're going to have a higher melting point and boiling point. You're going to have a stickier substance, so you're going to have higher viscosity. You're going to have more surface tension and more cohesion. That's like an attraction between the molecules. So when you have strong IMFs, you are going to have high melting point, boiling point, surface tension, cohesion, Or am I just scroll? Or am I trying to like smush everything into the corner? The adhesion is going to depend on what substance we're talking about it attracting to. So I'll leave that out of my list. Viscosity. Viscosity is a resistance to flow. It's how sticky it is. Sticky. But, okay, so a strong IMF is going to give you high of all of those things, but it's going to give you low vapor pressure. And we'll talk about why that is another day when we talk about vapor pressure. Okay, so and listen, don't memorize those lists. Just think about it. Like if something has a strong IMF, it wants to stay together, right? Wants to stay together, more likely to be a solid or a liquid, and going to be harder to melt, harder to boil, harder to flow. Any questions so far? Okay. I'm a little scared to scroll to the left. I'm afraid people are going to be like, ah, I'm not done writing. Are we done writing? Let's pause. And then we'll diagram it. Okay. So a dispersion force is generally your weakest intermolecular force. And the reason why it's weak is because it's temporary. The attraction between, or the creation of the positive and the negative is temporary. And it depends upon two molecules or atoms being near to one another. Okay, so when one atom comes near another atom, the electrons in this atom don't want to be near the electrons in this atom. And so they're going to move away. They're going to disperse from one another. That's why it's called the dispersion force. So if we look here at this first diagram, you guys, so like in atom A and in atom B, it's probably really hard for you guys to see. It's not the best diagram, sorry. The electrons are evenly distributed, right? They're like on both sides of the atom. And over here, they're evenly distributed on both sides of the atom. But if they start to come near to one another, you're going to have this repulsion between these electrons. And so the electrons in this atom, do you see how the electrons have all sort of like scooted over to this side? That's going to make this side of the molecule, or atom, sorry, partially negative. This can happen with molecules. It can happen with atoms. These are atoms. And so when this side becomes partially negative, this other side will become partially positive, which is then going to cause these electrons next door to shift over to this side of the atom. And so this side is going to become partially negative, and this side is going to become partially positive, and voila, you can have this attraction between positive and negative. Okay, or you can see it here with like the shading, like so the blue area is showing negative and the red area is showing positive. And so this force of attraction between that temporary dipole, that right there is your dispersion force. Oops. This is your dispersion force. And so I would diagram it, actually, let's just go ahead and diagram and then we'll watch the video. I would diagram it like so, right? So if I have, call this, H2, I have a hydrogen bonded to a hydrogen, right? So that's like you would originally just have sort of like this even distribution of electrons. And you have another hydrogen molecule with like an even distribution of electrons. When these two molecules come near to one another, this whole electron shifting thing is going to happen. And so it doesn't matter whether they go left or they go right. In this case, the electrons shifted to the right. Here I had drawn the electrons shifted to the left. Totally doesn't matter. So here, now we've got this, so if you're going to go to draw it, see, these are those stupid little peanut shapes that I can't draw. You get an uneven distribution. You get this partially negative area over here, larger electron cloud where the electrons have shifted to, and a partially positive area over here. And you get this partially negative area over here and a partially positive area over there. Again, these dots are my nuclei. And now we have this attraction between the positive area on one molecule and the negative area on the other. Okay, so that right there is your dispersion force. All right, now let's define what a dispersion force is, okay? I'll just use this as my definition. A dispersion force is a force of attraction between the partial positive and partial negative poles of a temporary induced dipole. And by induced, it means like made to have happened, right? Like if you induce labor in a pregnancy, you are making those contractions happen using a medicine. Okay, so the induction of the dipole happens when these molecules come near to one another. That's what's inducing the dipole. But because it is temporary, that's what makes these things pretty weak. These are like relatively weak. Okay, so because they are temporary, they are relatively weak. But like I said before, they can be made stronger by some of these key factors that I was talking about. So what would make a dispersion force stronger? So these can be made stronger with the presence of more electrons. Like if you have a bigger atom with more electrons or a bigger molecule with more electrons, the more electrons you have shifting, the bigger the partial positive or the bigger the partial negative is going to be, because you've got more charge moving around that molecule. We call that polarizability. When you have the presence of more electrons, the electron cloud is more polarizable. I like to think of it, or sometimes they even talk about it this way, of like the squashiness of the electron cloud. Like if you have a big cloud of electrons, it's like really like a squishy, squashy, polarizable electron cloud. They shift one way, you get a lot of negative charge shifting in one direction. And so you get a big negative in one area and a big partial positive in the other area. And the easiest way, I mean, is to just look at molar mass, right? Like if you have more electrons, you're going to have an increase in molar mass as well. So increase in molar mass means more electrons, means the more polarizability you have in your electron cloud. The other thing that can make a dispersion force kind of strong is surface area. The more surface area you have can make the dispersion force stronger. Okay, so it can be made stronger by, number one, more electrons. Number two, more surface area. Like long, linear carbon chains. Okay, the more surface area you have on the molecule, the more places of attraction you can have between the molecules. Okay. there anything else I want to talk about dispersion before we watch the video? Okay, so like I said, because this is like a movement situation. Yeah, my mouse is really acting up. I think it's helpful to watch a video. Plus, this guy's kind of funny, I think. So.
Positive metal ions in a sea of electrons in liquid helium. So here are two helium atoms. The little flashy green lights are indeed electrons and neutrons and protons in the nucleus. And if I slow time down and then stop it, you can see on the left-hand atom, the electrons and protons are on different sides, giving a temporary dipole to the atom. And those electrons repel the electrons in the adjacent helium atom and can lead to the formation of an induced dipole. And where you have negative next to positive, you will get an attraction, and that is the London dispersion force. It only lasts an instant because the electrons are soon on their way again and the attractive bond is broken. Looking down group 17, the halogens, literally giving birth to salt. Ooh, I bet that would sting. Notice the trend in boiling points there. Fluorine's a gas, but at the other end of the group is iodine, the solid. Why is that? Well, it's to do with London dispersion forces. The more electrons there are, the more London dispersion forces there are. And so iodine has more electrons than fluorine, and that has more London dispersion forces and a higher melting and boiling point. You need more energy to break those bonds, a higher temperature. So, London dispersion forces.
This part is so
these
funny.
Morningstar Farm sausages.
Why is it cooking sausages? There's a point. There's a reason.
That's about as disappointing as you can imagine. And then we've got veggie meatballs as well. Okay, they look a little bit better. So I'm going to pretend that these are pentane, and this is 2,2-dimethyl propane. So come over here and video the cooking.
Please.
Please. So you can see that the sausages and the meatballs have the same volume, but they do have different surface areas. This has a smaller surface area, it's a sphere, and this has a larger surface area. So the sausages, there are more points of contact between them, which means they're going to stick together more than the spheres that are only going to touch at very small points of contact. And the reason for that is that sausages have a larger surface area, meatballs have a smaller surface area. And it's the same with London dispersion forces. The pentane has a larger surface area, and the 2,2-dimethyl propane has a smaller surface area. So this is having a higher boiling point, and these are having a lower boiling point. Let's start the video. You know, actually, they taste like 2,3-dimethyl propane. So looking at this animation, you can see two molecules. Both of them have the same volume, but they do have different surface areas. The spheres on the right only make very, very small contact with each other, which means that London dispersion forces are going to be much reduced compared to the sausage shapes on the left, where there's much more contact when they collide each other. And rather labouring the point, here is the boiling point of pentane. You can see that it is indeed elevated.
Okay. You're welcome that you had to watch that. That cracks me up. I don't know why he's cooking sausages as the demo. But it does kind of get the point across about how surface area can, in fact, affect how polarizable and attracted these substances can be. Last thing about dispersion forces before we move on to dipole-dipole, and that is talking about what types of substances experience dispersion forces, okay? All molecules and atoms experience dispersion. All of them. Polar, non-polar, they all experience dispersion. Oh, I'm actually glad we watched that because he reminded me these are also called London dispersion forces. They are also called van der Waals attractions. So London dispersion forces or van der Waals forces, all the same thing, or just dispersion. Now, while all substances experience dispersion, so like even water molecules experience dispersion forces, we typically only talk about the force that is the strongest in a substance. So like, yes, water experiences dispersion, but the hydrogen bonds are a much more predominant or important factor in determining water's properties, okay? However, even though all molecules experience this, dispersion forces are the only forces that non-polar molecules experience, okay? So while polar molecules can experience dispersion and do, the only force that non-polar molecules feel is dispersion. So it is the, again, with the scroll, just scroll. It is the only IMF that non-polar substances experience. Okay, and I know it feels like we spent like a long time on that. The other ones are going to go a lot faster. Because really the other forces are the same thing as dispersion forces, but it's not a temporary dipole anymore. Like it's like permanent dipoles. So if you have a substance that already has a partial positive and a partial negative because it's a polar molecule, guess what that attraction is called? It's not called a dispersion force. Now we call it a dipole-dipole, but it's the same thing. So instead of, H2, where we were talking about a non-polar substance, let's say we were talking about like HCl to HCl. The chlorine is more electronegative than the hydrogen, so the electrons are going to get pulled in this direction. You're going to get this partial negative over here. And same thing here, this molecule is also polar. You got the partial negative over here, the partial positive over here. So like this electron cloud, they did it with colors here, but you could also do it with the stupid little drawings that I've done, where the electron cloud gets bigger around the chlorine, it's bigger around the chlorine, and smaller around the hydrogen. This force of attraction between them, between the permanent dipoles, is called a dipole attraction or force. So if we wanted to define it, just like we defined dispersion up above, a force of attraction between the partial positive and partial negative poles of permanent dipoles in polar molecules. So like, I don't even need to write a who experiences this paragraph. It's just polar molecules. They have to be polar for this attraction to be called a dipole-dipole. And because it is a permanent dipole, it is usually stronger than dispersion. Usually. right? But remember, if we had like a really squishy, squashy, huge electron cloud, or we had a really long carbon chain with a ton of electrons and surface area, dispersion could be stronger, but usually a dipole-dipole attraction between two molecules of similar size, the dispersion is going to be weaker than the dipole-dipole. Okay, so when you go to compare, these things, the dispersion force can only be a lot stronger if it's a much bigger molecule. If you're talking about molecules of the same size, the dipole-dipole is going to be more predominant or stronger, because you have this permanent dipole situation. These can also be made stronger. Can be made stronger with larger dipoles, like bigger differences in electronegativity values gives you a stronger dipole, larger dipoles, larger differences in electronegativity values. Right, so the bigger the magnitude of this vector here between your hydrogen and your chlorine, the more partially negative this is going to be, the more partially positive this is going to be. So that's how these things get made stronger. And in fact, that leads us directly into our next conversation about hydrogen bonding. So like, this is hydrogen to chlorine. But if you have hydrogen bonded to fluorine, fluorine is even more electronegative than chlorine. So you're going to get like a really big partial negative over here and a really big partial positive over here. So if you had another HF molecule next door with a really big negative and a really big positive, this force of attraction between the fluorine and the hydrogen, this dipole-dipole is going to be stronger than this dipole-dipole. Why? Because this negative is bigger and this positive is bigger, right? And we know magnitude of charge is one of the factors in determining the electrostatic force of attraction between them. When this is so super duper strong, we stop calling it a dipole-dipole and we start calling it a hydrogen bond. And it's a bit of a misnomer. I know it's not a bond like a bond between atoms, but because it's such a strong IMF, they call it hydrogen bonding, right? But it's not the covalent bond. Do not confuse it with the covalent bond. And of course, water is our most famous example of hydrogen bonding. So let's go ahead and define hydrogen bonding. This is a super strong dipole-dipole. And it is the force of attraction between the partially positive hydrogen atom and this hydrogen atom has to be bonded to nitrogen, oxygen, or fluorine. Okay, these are the three most electronegative atoms on the periodic table. These are the ones that are going to give you your strongest dipole. So the force of attraction between the partially positive hydrogen atom that is bonded to nitrogen, oxygen, or fluorine in one molecule to the partially negative nitrogen, oxygen, or fluorine bonded to a hydrogen in another molecule. So like, it doesn't have to be a water molecule to a water molecule. You could have a water molecule attracted to HF And that would be hydrogen bonding as well. So as long as in each molecule, you have hydrogen bonded to a nitrogen, oxygen, or fluorine, that's going to create a dipole that's big enough to create a super strong dipole-dipole attraction to another molecule. Okay. So we can see here in our water example, here's my partially negative oxygen being attracted to my partially positive hydrogen in the neighboring molecule. Okay, so you have this hydrogen bonded to an oxygen, attracted to an oxygen that is bonded to a hydrogen. I don't know why I circled them. Here's your IMF. That's your hydrogen bond. That's your hydrogen bond. That's your hydrogen bond. That's kind of a weird way to draw it. If you wanted to just draw it with some Lewis structures, here's this is probably an easier way for you guys to draw it. Here's one water molecule. Here's another next door. We know that the oxygen is going to be partially negative. The hydrogen is going to be partially positive. Partially negative up there. Partially negative up here. The hydrogen bond is the attraction between this hydrogen and this oxygen. Often there's a lone pair there as well. See that lone pair there? Okay. When there are lone pairs there as well, and in this case, you guys, for every hydrogen, there is a lone pair. Like water is unique because it's like got this perfect one-to-one alignment because there are the two lone pairs on the oxygen and there are two hydrogens on the neighboring water. So when you get this like perfect alignment between the numbers of hydrogens and the numbers of lone pairs that you have available, this is called perfect hydrogen bonding. And it's like super duper strong. And if we were in school, I would be showing you some fun little demos with that. We'll just have to wait till tomorrow. Like the hydrogen bonds are so strong that like, well, I'll just wait and show you. I've shown you before. Okay. We have one more to talk about. Okay. I forgot to talk about strength. These are generally the strongest IMF. And again, dispersion could be stronger if you had a really huge molecule, but for molecules of the same size, your hydrogen bonding is going to be stronger than the others, than dispersion or dipole-dipole. How can we get, how can hydrogen bonds be made stronger? Obviously, just like dipole-dipole, the bigger differences in electronegativity that you have, like the larger the dipoles, the stronger the hydrogen bonding. So same as dipole-dipole. Or like I was saying here, in the case of water, if you have this perfect one-to-one alignment for every lone pair that you have on your negative partial charge atom, aligning with every partially positive atom that you have next door, every partially positive atom in the molecule next door, that can make your hydrogen bonding stronger as well. So it's generally the strongest and is made stronger by larger dipoles and lone pairs. Okay. We've made it to our last intermolecular force. These are your three main ones that I said at the beginning. This next one is a little bit different because it's a force of attraction that happens or is created when we dissolve things in water, when we make a solution between something that's ionic and something that is polar covalent. And so we've talked about this a million times, but we haven't exactly like named it as a particular force. You found it? Oh my God, you guys. Oh my God, hang on. I have to. Okay, So last force of attraction, again, this would not be with like a pure substance. This would be like with a mixture of substances or a solution. It's just like what it sounds like. An ion dipole attraction is the force of attraction between a dissolved ion in solution and its polar solvent. Right, so where is the attraction? Well, an ion has charge and the polar solvent has charge. Typically, the polar solvent that we're talking about is water. Okay, so this example here shows the sodium attracted to the oxygen, the partially negative oxygen in the water molecules. So you can see the orientation of the molecule as all of the oxygens are attracted to the sodium. But what if I had a chloride ion in there as well, like the salt that I dissolved with sodium chloride? The orientation of the water molecule would be flipped in this case. And the force of attraction is the same. Oh my God, that's a disaster. The force of attraction would be the same. It's still called an ion dipole, whether you're talking about the attraction between the negative to the positive hydrogens or the positive to the negative oxygens. So the force of attraction here is the same as the force of attraction here, and it is called an ion dipole attraction. And of course, we know that these can be made stronger or weaker, right? We know some things are soluble and some things are not soluble. Like, so the more soluble the substance, the stronger the attraction is between these solutes and solvents. So what would make this attraction stronger would be the size of these ions. Made stronger by the size and magnitude of charge, of the ions. And if you're like, well, why? Anthony's favorite equation. Anthony, are you awake? This equation, which is Anthony's favorite equation. The reason why the magnitude of the charge matters is because, like, that's what those Q's are, right? So the bigger the charge on the ions, the stronger the force of attraction between the water and the ions. And the smaller the radii. The smaller the radii means the greater the magnitude of charge, because when the ions are small, those water molecules can snuggle in real close and you can get attractions between the, you can get stronger attractions between the cation and the oxygens, or the anions and the hydrogens. So magnitude of charge and size of those ions is going to determine how strong those ion dipole attractions are. And that's it. The problem sets that I have assigned are a little bit hefty, as in, like, there are a lot of problems. It's just because that's how important this chapter is. So I apologize that there are a lot of problems, but, like, we need to do the practice because this stuff is really important. And I do have that answer key for this problem set. I'll post it this afternoon. So do those problems this afternoon. Check your answers. If you need to, like, spread the work out over the course of the week, that's fine. But, like, please, please, please do the problem set.